Okay, so we're going to start with talking about antiderivatives. This is section 4.9. So this is antiderivatives. So what we'll say is we need to define this first. So definition, we'll say a function, and we'll use capital F to denote it, is an antiderivative of f of x on interval a to b if you take the derivative of that function, it equals the little f of x for all x in a to b. Okay, so we'll look at a quick example. So let's say for this example we got say find 3 antiderivatives of, let's say, 2x. So I need to come up with 3 functions that when I take their derivative give me back 2x. So I could say f of x equals x squared. So I take the derivative of x squared, I get 2x. Well, the other types that are going to work are all going to be based off this x squared. What we're going to use to get the other two is, if I have x squared here, I could put a random number here like x squared plus 3. And since the derivative of 3 goes to 0, the derivative of x squared plus 3 would still just be 2x. And I could also do one over here like with a, say x squared minus 4. That would also, derivative of negative 4 goes to 0. So here's 3 possibilities that would work. And we can see they're all kind of based off this x squared. They're all x squared either plus a number or minus a number. So we're going to use that in our next bit when we go through to define the next thing, which is going to be a theorem about an antiderivative. It's going to use that idea. So we're going to let f of x be an antiderivative of f of x on interval a to b. Then every other antiderivative on a to b is of the form f of x plus c, where c is some constant. So from the previous example, if we had f of x equal 2x, and we said, well, capital F of x equaled x squared, then the general antiderivative would be x squared plus c. This would be every possible, you would use a different number in for c each time, but this would generate all possible antiderivatives of 2x. So these would be all possible functions that when you took their derivative gave you 2x. So we're going to go through and look at a couple of this. So another example is going to say find 2 antiderivatives of f of x equals cosine of x. Then find the general antiderivative. So we need something that when I take its derivative becomes cosine. Well, the derivative of sine is cosine, so I'll make one of them sine of x. Here's one of my antiderivatives. The other one, let's do sine of x plus a number. So sine of x plus 1. That also has derivative cosine. The general antiderivative will be sine of x plus c, where c is able to be any constant, so c could be any number we wanted to put in there. So here's our two antiderivatives and the general antiderivative. Okay, so next little topic here is notation. We say the notation, we got this integral symbol, f of x dx equals the antiderivative of x plus c, means that the derivative of capital F of x equals little f of x. So we say capital F of x plus c is the general antiderivative or we could also call it indefinite integral of f of x. So this is another way to write the general antiderivative, and we would refer to that as the indefinite integral. So we're going to stop on part 1 right here. We're going to pause on part 1. Part 2, we'll look at evaluating the indefinite integral and finding a couple of examples of it.